Welcome everyone. I'm Yonik Seeley. I created Solr way back in 2004 now, while working for CNET Networks, and CNET had the foresight to contribute it to Apache, and then I helped co-found Lucid Imagination in 2007 to be the commercial voice behind Lucid and Solr. I'm going to be talking a little bit about what faceted search is, how Solr implements it, some tips and tricks surrounding it, and also some of the algorithms and the performance characteristics that we use behind the scenes. I took a lot of these slides from one of Haas's talks. As a result, I have too many slides, so I'm really going to have to burn through this stuff. So could I get a quick show of hands? Who has used Solr faceting before? Okay. How about the reverse? Who has not used Solr faceting? All right. I'm going to burn really fast through some of these beginning slides then, because this is going to be boring for you. Blah, blah. So what is faceted search? This is just a screenshot from CNET reviews, just a little vocabulary overview. We have our facets at the top. We have our document list at the bottom that I sort of cut off for showing the top 10 documents. So a facet is just a way of categorizing results. The constraints are the individual values under a facet. That's the normal terminology we use in Solr land, or else facet values sometimes we use. And we normally have a count next to it. So key elements of faceted search are that no hierarchy of options is normally imposed on you. You can add or remove the facet constraints in any order. And there's no surprises, of course. There's no dead ends. You don't have to select an option to see if there's any matches under it. Because you have the little count, you already know how many items match. And normally, if there are no items that match, the label will just be removed altogether. So Solr's faceted search, I can skip over this really quick since it really nobody has not used Solr's faceted search. Wow, okay. This is a faceted search response. Or if you prefer JSON, stick a little WT equals JSON, because some people, I don't know if Simon's still here, don't like XML anymore. So yes, you can get it in JSON. And then just a little overview. When the user clicks red, normally we just you add to drill down in your facets, you add a FQ, a filter query, color : red. And in this case, since our field was single valued, we removed the redundant facet field on color, because we know that we drilled down. We know that we're getting back all things that are red already. So it would be kind of redundant to facet on the color field anymore. So some facet.field options. If you can specify a prefix of things that the constraints that you're interested in. Only return constraints that start with this prefix. Min count just says the minimum number of the minimum that you're interested in for constraints. Sort is either count or index. Counts by default, of course, highest first. Index is lexicographic order in the index. And this means it's normally like alphabetic order, or for numbers, the way they're indexed, it actually returns the natural numeric order. Offset and limit can be used to page through large facet results. And adding missing just will give you a count for the number of documents that don't have any value for that field. We have facet.query, of course, which I assume you guys all know about. And just a reminder that the label used when you do a facet.query, which just takes any kind of arbitrary query, it just comes back as the label is the whole query itself in the response. So for facet.query, you can do some cool things like spatial faceting. We have spatial search in Solr now. And so hopefully you've seen the local param syntax, the curly brace bang, geofilt. So geofilt is our geospatial query, normally used as a filter query. And by default, it looks at some global parameters like the PT is the point that you're searching from, the latitude, longitude. And S field is the spatial field, short for spatial field. And that just contains the field name that you're comparing against, that has all the spatial data in it. It's of type, lat, lon. And so we do 2 facet queries, one with a distance of 5 kilometers and one with a distance of 10 kilometers. And you can see in our result, we determine that there are 3 things within 5 kilometers and 6 things within 10 kilometers. This isn't the fastest way, but it's currently the only way. In the future, I think we probably want to do something like facet by some kind of faceting on function queries, and we also have geodistance function query. And so that would allow you to that would allow Solr internally to only compute distances once. In this example, it's really going to compute distances twice, and so it could be more efficient. But some people are actually already using stuff like this. So we have range faceting, of course, where instead of just having a whole list of facet queries, you can specify a start, an end, and a gap, and then Solr will just compute all the buckets for you. And in the response, what comes back is the starting point for each bucket. And so you can calculate yourself the ending point by just adding the gap. So date faceting is now deprecated because you just use range faceting on a date field. And so this is sort of an interesting example because you can use date math. And so you can handle all the weird things like months having different numbers of days, leap years, and things like that, where you couldn't do it if you were just operating on milliseconds or something, or couldn't do it easily. And so in this example, if you haven't seen date math before, our starting point, now/year, that rounds to the year 2011, minus 1 year, so 2010. So our starting point is January 1st, 2010. The ending point, now/month, October, plus 1 month, November. So November of this year, the 1st of November this year is our ending point. And our gap is plus 1 month. And you get a response like this. An interesting thing to note is that you can actually use date math when trying to construct a constraint. So you get this response back, you display it to the user. What happens when the user clicks on one of these labels? Well, you want to construct a filter query to send back down to Solr to drill down. And so what that filter query would look like, you could just do a range filter on your date field, right? And the starting point would be just like right from the label, or right from the starting point that Solr returned to you. The ending point, you don't have to calculate that yourself. You can use date math. You can use start point and then just append the gap. So the start point plus 1 month, and then Solr will calculate what the actual endpoint is. Just some esoteric parameters that you might not know about, even if you do know Solr faceting. The hard end parameter sort of tells you how to treat that last bucket. Because the endpoint may be here, and you may have gap, gap, gap. So the endpoint may be, you may have a smaller bucket on the last endpoint. So like hard end really says whether you should allow that smaller bucket or not. Facet.range.other, that's just other things outside of the bucket. So like everything before it counts for everything after, things like that. And then facet range include equals lower. That tells you how to treat the bounds. So lower is the default, and so the lower bound is inclusive by default, and the upper bound is exclusive. And that's what actually we wanted as a default for our date faceting. So for example, the last month, October 1st to November 1st, well, you really just want all things in October. So that's what that does, essentially, by making the November 1st exclusive. Pivot faceting is something that's currently on trunk. And that really lets you sort of compute a matrix of counts. And you can pivot on any arbitrary number of fields. And it's sort of a matrix. It's a sparse matrix. It'd only be a full matrix if you asked for it to be, because it's based on like the top, for each pivot, it's based on the top number of results. So in this example, pivot on cat in stock. We can see that cat electronics matches 14 docs. That's the top value for a category. And then under that, we pivot on that, and of those, 10 are in stock and 4 are out of stock. And here's just what a JSON response looks like. In this example, it's cat, popularity. And so you can see how the response is structured. First, we take the top value for category, which is electronics. That counts 14, and then we pivot. And so then for the popularity field, the top value that also has electronics is 6, and there are 5 of those. And so then we go through all the popularity field, or all the popularity constraints, and then we go to the next highest value for category, which is memory, and so on. So term query parser is something that's really useful to use with field faceting. So with field faceting, you're getting these arbitrary terms out of the field, and they're being returned to the GUI. And the GUI, if the user clicks on it, they have to send it back down to Solr in the terms of a filter query. Now, by default, the Lucid query parser is used. Now, that has syntax and stuff, right? So if your term has stuff that Lucid would consider query parser syntax, you'd have to escape that. And that can be a little bit of a pain. So one thing we've done to make it easier is the term QParser. Again, we use that local param syntax, curly brace bang. And so the term QParser just takes whatever is after it and just makes it a term, and there's no parser syntax at all. So there's never anything to escape. You can just append the raw term value right after. And the F just shows what field you're making the term for. And you can even use parameter dereferencing if that makes your life a little bit easier. These two are equivalent. So V is normally what comes after the local param stuff. And so you can say, instead of looking after, instead dereference, look for another global parameter, request parameter T that contains my term. Taxonomy facets are cool. We don't have native support in this for Solr yet. Hopefully we will in the future. But so let's assume we have like document 1 that is on node law. We have this hierarchy, a taxonomy. Document 2 is on the middle node, science. And document 3 is on both physics and history. Now we can flatten this information and represent it as sort of like a path. So for instance, that document 1 that was on the law node, we'd represent it as nonfiction law. So that's the path. And now we can do some pre-processing or come up with a custom analyzer. It wouldn't be too hard to do this for us. And what we want to do is index a token for every length of path starting at the root and going to the node. So for our nonfiction law document, we first index nonfiction by itself, and then index nonfiction law as another token. And additionally, we prefix this token with its length, the path length. And we'll see why on the next slide. And so this is how we query it. So we do a facet.field on our category field that contains those terms now. And we do a facet prefix. And we say we're only interested in things that start with nonfiction. But here's the catch. We're only interested in things that start with nonfiction that have a path length of 2. And so what that will give us is just the direct descendants, just the direct children of the nonfiction node. And you can see in the response that we have 2 under science, which if we remember, one was directly on the science node and one was on the physics node below that. And how we indexed those, both document 2 and document 3 had that nonfiction science because we indexed all of the path links up to the node. Now, if the user clicks on that science node to expand it, say they want to like drill down, right? Here's how we do the drill down. We do the normal filter query on the nonfiction science node. And then we do a facet prefix on nonfiction science. except we say now we're only interested in paths of length 3. And so again, that'll give us just the direct children of nonfiction science. And we can see that in our response, we actually get the document that's below science. Now you notice it's like the count is 1, and that's because we did not include the document that was actually on the science node. They would still come back in the document list. Depending on how you want to represent it, you could actually have like a self node under it. There are a lot of tricks depending. So multi-select faceting is another cool thing that we added support for back when we were trying to put together Lucid Find, which is just a little search tool for Lucene and Solr resources. And so we realized that, like, well, if I'm trying to look for something I wrote a long time ago or something I don't remember, it could have been in the Lucene mailing list or the Solr mailing list. I really want to select both. And this is called multi-select faceting. And the same for source. It's like, I can't remember. Was it in a JIRA comment or was it an email? So again, we wanted to let people select more than one constraint under a facet. And how we really want it to work is when the user clicks on, say, the Lucene constraint, we want to leave all the other counts up there. We don't want to, like, remove them, even though we've constrained to Lucene, because the user may select another one. And likewise with source. If they click on something in the source facet, we don't want to, like, remove any of the other counts in that source facet because the user may click on another one. Now, the trick is we do want everything else to change. When you click on Lucene, you don't want any of the counts under the source facet to change, the project facet. But you want everything else to change. You want the numbers in the source facet to change, and you want your document list to change. So when you think about it that way, when you facet on the project facet, you really want to say, just sort of disregard any constraints that have to do with the project facet. And so we came up with a very generic method to enable us to do this multi-select faceting. And it reuses local param syntax. And we added the ability to tag filters and to exclude filters when you're faceting by any tag. So here's our query on the right-hand side that sort of reflects what you see in the GUI. And so we have our query for index replication. And now we have our FQ, or filter query, for project Lucene or Solr, because they're both checked, so we're interested in both. And we've tagged that with the local param syntax, the curly brace bang, tag equals PR. And that's just an arbitrary string. It can be anything. And then when we facet.field on the project field, we say exclude any filters tagged with PR. And it actually can be the main query even too. We allow that now. And then when we facet on the source field, we exclude anything tagged with source. There isn't anything in this example, but that's okay. It doesn't throw an error or anything, because just to make your life easier, because there would be if you clicked on anything in the source facet. And yeah, so that's worked out relatively well. The one thing we haven't added yet, just the teeny little downside, just as an aside, since I did blow through those first slides so fast, are filter queries that we normally cache separately. We don't have a way to cache the subclauses separately yet. So every time you click on an additional project, you'd add an additional, like Lucene or Solr or Nutch, say. You're not going to get good caching. It's not going to cache Lucene independently from Solr. It's going to be one query, Lucene or Solr or Nutch. So that's one thing we can add in the future, just a special query type that would cache, a disjunction query type that would cache the filters independently, its disjunctions independently. So there's another parameter we added called key, because you can do things like facet on the same field with different exclusions, since this is a much more generic method than to just support multi-select faceting. And so if you do that, by default, what comes back in your response is keyed off of the field name. Well, if you facet on the same field more than once, then you can't tell them apart. And so we introduced the key parameter, and so you could change the label that appears in the response. In this example, we're querying for hot rod. We have our filter query. That DF, that's not often used. So if you don't know what that stands for, it's just the Lucid default field for the query parser. So when you don't specify an actual field : value, it uses the default field. It normally gets that from the schema, but you can override that in local params too. And we tag it with CX. And we're restricting the things that are purple or green. And so then our first facet field, we facet on colors, which is multi-valued for this example. And we exclude that filter. So this is really faceting over all colors of things that match hot rod. And then we facet again on the colors field, but we leave that constraint in there. So this is things that are purple or green. And then we also want the other colors that are in there. And you see we get the labels in the response. And so then, you can do interesting things with this, like I guess you could say, of things, red things, there's 7/19 of red things that also have purple or green in them. So just the other random type of statistics you can calculate with this exclusion stuff rather than doing multi-select faceting. Say that you have this category field, right? And it's normally used for full text search. And it works fine for that because there's a lot of text processing on it. But it may not be suitable for displaying to the user as a constraint label. So one trick is to use copy field, copy it into a different field, and do a whole bunch of processing on it to make it look pretty. So in this example, say it was a comma or semicolon delimited list of categories. You have this category field. And so this first pattern tokenizer splits things out by comma or semicolon. We clean up spaces. We replace and with ampersand. We trim trailing or leading white space. And then we change the capitalization so that each letter in the string is, each word in the string is capitalized. So title capitalization. And just a little example of copy field and how this would work then. So if we index a document and have this messy categorization field, and we have this copy field in the schema that has the source of category and the destination category pretty, it goes through all that processing on the previous page, and then if we facet on category pretty instead of category, then we'll get these nice labels out to display to the user. So another little tip related to labeling for the user is to realize that any kind of parameters in a facet query are echoed back to you in the response. And so you could think of like if you have this, you could have a GUI that label meant something to, as in, use this for the label for this facet constraint. And you could define a facet.query for like a hotness factor in your Solr config.xml as like a default or something in a custom request handler. And so when your UI queried Solr and said facet equals true, it would get this back. And it wouldn't know what the query was, but it wouldn't have to. It could just deal with it because it has the label. And it comes back with the complete query. And this query, this is just an example of it has to have some popularity and had been published within like the last day. And so the UI can be sort of a dumb UI. See this label, use the label, but when the user clicks on it, just echo back the whole big query, and it'll work in Solr. See that key parameter? You might think about using key for facet queries, and that will work. But the problem is that's all you'll get back. If you said key equals hot, well then your UI would get hot as the label, and your UI better understand what that means, right? If the user clicks on hot, what filter query do you use to send back down to Solr? Okay, performance, on to my favorite part. I tried to summarize it a bit in a table here. When you use facet.field, there are currently 4 different underlying implementations that are controlled with facet.method, different ways that these constraint counts can be computed. But I have slides on all of these, so I'm going to skip over the summary and go right into the meat of it. So facet.method equals FC, stands for field cache, on a single valued field, uses a Lucid field cache entry at the top level of the index. And so as far as memory, there's an int array that just of size maxdoc that holds the ords, and then you have to have room for all the unique terms too. And so that's about how much memory it takes up. And as far as CPU, it's big O of the number of docs in the base set. Because the algorithm is really simple. We just step over the docs that match the query and the filters, right? We go and look up the ord and then increment that slot in an accumulator array. And then when we're all done, we shove the whole thing through a priority queue to find the top 5 or 10 constraint counts. So there's one disadvantage, though, of using a top-level Lucid field cache entry, and that is near real-time. Lucid uses a segmented architecture, so it has multiple segments in the index. And normally what happens when you add a couple documents to the index, this new little segment gets created. Now, if you have a top-level field cache entry, you have to recreate the whole thing whenever the index changes. If you instead cache that field cache entry on the segment level, then you really only have to regenerate those entries for the segments that change. And even more specifically, they can be reused if there's only deletions too. So the facet.method equals FCS is just the plural of FC because we cache at the segment level. And it's very much like the top-level field cache method, how we count up, except we have an accumulator per segment, and we can actually count in multiple threads. The big downside to this method is that we have this extra item here, this accumulator merger. Because we have these multiple accumulator arrays now, the problem is that the ord in segment 1, like say ord number 0 in segment 1, isn't necessarily the same as ord number 0 in segment 2. Those counts are maybe for different strings. And so you actually need to merge all of the field cache accumulators. And that is expensive. That actually takes more time on average than the counting itself. And so you really only want to use this method when you have a rapidly changing index. And when I say rapidly changing, I mean rapidly being committed, rapidly trying to view new snapshots of the index. Because you can add documents all you want in the background, and that's fine. It's only when you do a commit or reopen the searcher that you're going to hit this big top-level field cache reload. So we can control the threading with local params again. You just put hash bang number of threads equals 4, and that'll just control the number of threads that are counting at once. And like I said, so the disadvantage is it's slower, and it's actually larger memory use too than a top-level field cache, because the strings in each field cache are not shared across each other. And the advantages, of course, is it's more near real-time friendly. So here's some time ago I did a comparison of per segment faceting versus the top-level method for a single-valued field. And as you can see, for the quickly changing index, the FCS method always wins. And when I say quickly changing, I was committing multiple times a second, really just back to back, just a little while loop and just commit, 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 commit. And if you don't have a scenario like that, then the old method, FC, always wins because of that merging. But the merge is big O of the number of terms. And so if you look in scenario B, there was only 100 unique terms. And you see that the FCS method had much less there was much less of an impact to that field cache merging. Whereas the scenario A had 100,000 unique terms, and you can see that it took a lot longer to merge those field caches. Okay, and so our first multi-valued algorithm is called uninverted field, and you get it when you do facet.method equals FC on a multi-valued field. And that's because it's really like the field cache method, but it uses like a multi-valued field cache called uninverted field. And so it's good when you have many unique terms, but if there are relatively few per document, because it's an uninverted field, just like a field cache, for each document it sort of has to list out all the values it has. So for full text field or something, no good. So in the best case, it was like 50 times faster and like 5 times smaller than the previous algorithm, which I'll cover next. But those are old values. I think we've also sped up the enum method. That's what this was in comparison to. And so, I mean, I don't know if it's like 5 or 10 times better today. It's probably still better, but the best case is probably a little bit less. It's big O of the number of docs, like I said, because it just, we iterate docs and then just like increment an accumulator array. But we also have an optimization where if the docs that you're counting, if it's over half of the docs in the index, instead we count the inverse. We count the documents that are not in the set, and then just like, because we've kept track of the maxes and everything, and so we can just do that logic. We did a lot to make it very memory efficient too. So the terms that belong to a document, it's an ORD list, but it's sorted, delta coded, and stored as like vints. And so the ORD list for any document can be packed inside of a single integer. It's like up to 4 ORDs in a single integer if they'll actually fit. Or if it doesn't fit, then that same integer will point out into a shared byte array. So again, there's a lot of compression here. It's a very specific compression to this problem, though. It's also a hybrid approach because if there are any big terms, and we define big terms as matching more than 5% of the index, we consider it sort of like a waste to try to uninvert all those term instances and try to record it in all the documents because we need at least a byte to represent a document in this, or represent a term in this scheme. And so instead what we do is we fall back and use the filter cache. And that will be represented as a bit set with 1 bit per document containing the term. And so that's a big savings there. And then the other thing is that we do not, unlike the field cache method, we don't store all the string values in memory. We only store every 128th string and use that as an index. And during all our facet counting, we always operate on term numbers and ORDs, essentially. And then only at the end, we have like the top 10 ORDs or whatever, and then we convert those back to strings. So the uninverted field method uses the field value cache. And so if you go to the admin page and search down for field value cache, you can sort of see the number of entries and a lot of information about it. The field value cache is not auto-warmed, so you should normally set up a static warming request for the facet fields that you're going to use with this method, unless you want to take a first-time hit, because that first creating this whole uninverted field can take some time. You can see some of the stats that you can see on the stats page. It actually shows, because these items are very big, the field value cache actually shows by default all the items in the cache. And so some of the information that's in there is the approximate memory size for every specific field, how long it took to uninvert, and the number of terms, the number of big terms, a whole bunch of interesting stuff that you can sort of look at and see maybe if you should be using a different faceting method or get an idea of what this thing's actually costing you. And the last method, which was actually the first method that was implemented in Solr, facet.method equals enum. It's called enum because it essentially enumerates over the terms in the Lucene index. And for each term, it asks the Solr filter cache, give me the doc set that matches this term. And then it creates, does a fast intersection count and shoves it into a priority queue. We've added a bunch of optimizations along the way. Well, one optimization is in the Solr filter cache itself. Just basically our filter representations. If they're big, they're bit sets. If they're small, there's a compact representation. But we also can short circuit by docfreak. Lucene can tell us, before we go and read the posting list or anything else, as we're iterating over the terms, Lucene can tell us what the docfreak was, basically the number of documents in the index that match that term. And so if we have a full priority queue, then we can compare the smallest item in that priority queue to the docfreak of the term that we're currently looking at. And if the docfreak is smaller, then we know it's just a waste of time to go ask the Solr filter cache for the set and then to compute the intersection, because we know that it can't possibly be big enough to make it into the top n that we're looking for. Another optimization, or more like a trade-off that you can do, is we allow you to specify a min df, where anything with a lower df than that, we're not going to go to the Solr filter cache, but instead we're going to directly use the Lucene index. If you noticed, it's actually the same information that's in the Lucene index on disk and in our filter cache. It's just the filter cache is faster and optimized for quick intersection counts and quick filtering. And so you could say, like, anything with a docfreak below 10 or below 50, don't go through the filter cache. I don't want to use that memory. Instead, compute the intersection count directly from the Lucene index. You want to size your filter cache appropriately. Because it is an LRU cache, if your filter cache is this big and the number of terms that you need to iterate over when using facet.method equals enum is a little bit bigger, what happens, because they're always accessed in the same order, your hit rate essentially will drop to 0 because it is the LRU cache. So it's not like it'll just drop a little bit, it drops off a cliff. So you really want to make sure that your filter cache is big enough. Another cool use case, though, for facet.enum is that you can get it to use no memory. This facet.enum.cache.mindf, that's the parameter I was telling you about. You can specify like a minimum docfreak below which it won't go to the Solr filter cache. So if you have this huge index with this huge text fields and stuff like that, and you really don't care about how long it takes, you can still get faceting to complete. You just jack up the mindf, and it just won't use really much memory at all. It'll be slow because it'll be stepping over a large part of the Lucene index, but it will complete and it will work. And I think this is probably the only faceting method that you can do that with. All right, and actually completed with time for questions, which I didn't think would happen.
Okay, so I have 2 questions. One of the questions involves the pretty display of the facets. So in your example, I wasn't clear if you copy the nice looking version of a category to another field, I wasn't clear whether you could get the pretty facet in the actual facets returned in the result, or if that only appears in the document in the result set.
It would depend on if you stored the field or not. So you would just, if you did a copy field from category to category pretty, and then you faceted on that, you'd get that back in the facet counts. But if category pretty was not stored, you'd just only get back, in your document list, you'd be getting back the normal category field, whatever is stored.
Right.
Oh, I'm sorry. No, you would not get that back regardless, because that's an indexing time. It's analysis, so this only affects what is indexed. It doesn't actually affect the stored field at all. So in the documents you get back, you would just get back the raw stuff. People have asked for like analysis for incoming things. It's a little bit different.
Yeah, because the pattern that we have in the past, and we're migrating from a commercial search engine to Solr, is we select on the normalized version of a category, which doesn't look attractive to a human at all. So in the navigator's return in ESP, we have all these ugly versions of these things. And in our migration effort over to Solr, we want to make sure that for the when we're displaying the faceting, that we're able to display the pretty version while still having access to the normalized version, which we have to use for the query. So it sounds like that is or isn't possible currently.
Yes, Haas is giving you the thumbs up. Yeah, I mean it's indexed twice here in the copy field.
Oh, okay. The other question that I have is, so I was actually quite pleased with the approach where you have the one/category, because that was something, kind of a hack we had to do before when we were looking at this. So it looks like the approach that you outlined, where the first thing in the category is the number of elements, it looks like that's very flexible. So it sounds like if you had something like motors, like you had a top level category called motors, and you had a secondary level category called DC, it sounds like you could use that mechanism for also providing faceting on arbitrary attributes that belong to a particular category. So like under motors and under DC, there might be RPM. And the RPM might have a value. So I can see that in that particular case, you might be able to say motors/DC/attribute name, which might be RPM/value. So does it sound like a viable approach for providing arbitrary attribute-based faceting for categories?
I haven't thought about it. I mean, it certainly sounds reasonable. Because you can certainly think of it as, again, just in a taxonomy, I guess, yeah.
Okay, cool.
There's many ways a Lucid query can be fuzzy, and that will produce a result set of wildly varying quality. How do we incorporate quality thresholds to make all of these counts have any meaning? And that's as much a usability sort of UI design question as an API question.
Yeah, we haven't done that yet. I mean, the obvious thing to do, and I think people have asked for this too, so I imagine it's going to come at some point, is, they want facets on their top 100 documents by relevance. That certainly makes sense, or top 1,000 or top whatever. And so that's what, I mean, I think, that sounds pretty easy to do. We've just never done it. We're just, even if you ask for the top 10 documents, I could see us having some parameters saying facet on the top 1,000 most relevant documents, and then we'd have to get that list.
The facet prefixes. Is there any way, so I can search for only facets starting with an A, for example. Is there any way to get the counts for all of the first letters, for example? So sometimes you have many facets and you want to show the most common ones and show a way to drill down.
Yeah, I mean, I guess, no, there's not a way to do that with a single out of the box. I mean, you'd normally just create another field for that or something with the first letters.
So you have a first letter field.
Right. But there's not, I mean, we could implement that, but it wouldn't be efficient. You sort of have to step over them all and then compare if that had the same. So you're really better off with a separate field with just containing the first letter anyway, I think.
Okay, one last one.
Hey, one question. Is it possible to Well, with faceting enabled, sometimes it happens that returning result takes twice as much time as without faceting. So, is it possible to bring result back first and then somehow get facets afterwards?
Yeah, I mean, I've seen people do that. I guess when facet's slow, we really try to make faceting sub-second so it can always come back with the request. But I have seen UIs that will basically do that with two separate requests. And with the caching and stuff like that, Solr would be, I believe Solr would be normally caching the doc set, or you could get it to somehow. You could get it to cache the doc set such that that first query would not be re-executed, but you could still use two separate requests. Well, you'd have to send one and then the other, maybe. If you sent them exactly in parallel, yeah, maybe one should still win. You could basically, yeah, two separate requests is the way to go. It's just the question of like, how much extra work you're doing by that or not, and the whole caching thing in there.
All right. Well, thank you very much, Yonik.